back. I'm using an older computer and it's got a little bit of lag. So this is part B of electron configuration. So it should pick up right where the last one left off. So we were looking at and comparing the Bohr model of an atom with the electrons in these rings or fixed orbit to the quantum mechanical or present day model where electrons reside in these probable regions of space called orbitals. And they have designations like 1s and 2p and 4f and so on. And then finally, I'll show you how this energy level diagram relates to the electron configuration. So we'll go through a few of these elements and you'll start to see the pattern. If we're to do hydrogen, hydrogen's atomic number is 1. And what that means is if you have an atomic number of 1, you have just one electron because you have one proton and one electron. So that first electron fits in the first orbital down here. And because it's in this orbital, we say 1s1. That means it's the first energy level. It is an s orbital and there's one electron present. In the Bohr model, the N here refers to the nucleus. And then in the first ring, there would be one electron. That would be hydrogen. Okay? So far those don't look really very different. Well, let's try helium. Helium's atomic number is 2. So remember, each orbital can hold 2 electrons. So that second electron fits in the 1s orbital. Notice it had to go spin down, right? And why did it have to go spin down? If you said the Pauli exclusion principle, you're right. Okay? They have to be spinning in opposite directions. So the electron configuration for helium is 1s2. You don't say 1s squared. It's not math class. It's 1s2. The first 1 represents the first energy level. Think of that as the first ring on the Bohr model or the first row on the periodic table. And they're filling up an s orbital with 2 electrons. Now, on the Bohr model, we just put 2 electrons in that first ring. We don't have to specify anything more than that. Notice they're not right next to each other because electrons do have a negative charge. They'll repel, and they'll try to be on kind of the opposite sides of each other. Let's move on to lithium. Lithium's atomic number is 3. That means it has 3 protons and 3 electrons. I don't want to end the show. I just want to go here. So, whoops, I jumped to carbon. Let's go back to lithium. So lithium has 3 electrons. Notice that it goes 1s2. That's full. Now we have to go to the next available parking spot, which is up here in the second energy level. The s orbital is available, and there's 1 electron there. So we write 1s2, representing these 2 electrons. Then we go to the second energy level, s orbital, 1 electron. So that's 1s2, 2s1. Notice it has 3 electrons total. How does this correspond to the Bohr model? Well, in the first ring, there's 2 electrons. First ring, 2 electrons. In the second ring, there's 1 electron. Second ring, 1 electron. So they're similar, aren't they? All right, let's go to carbon. Carbon's atomic number, if you were to look, is 6. So that means it has 6 protons and 6 electrons in an atom. The filling order is going to go 2 in the first energy level. That's full. Then it goes to the 2s, 3, 4, and that's full. And then, of course, it goes 5, 6, 1 in each of the p's. Why don't we put 2 in 1? Well, that would violate one of our rules. So we always want to make sure everybody gets 1 before we double up. Do you remember the name of that rule? Hund's rule. Good. No, we don't say urinal rule. It's the Hund's rule, but it has a U in it, and that helps us remember that. Now look, in the Bohr model, 2 electrons in the first energy level. That's what it says, 1s2. In the second energy level, notice there's 2 s's and 2 p electrons for a total of 4. In the Bohr model, we just put 4 electrons. We don't specify any further than that. Let's keep going. Nitrogen. Nitrogen has an atomic number 7. So when we put in the electrons, it goes 1, 2, 3, 4, 5, 6, 7. Each of the 2 p's get a single electron before anybody doubles up. If you end up going to West Point or one of the military academies, it's all about team. If there's 12 hungry guys at a table and there's 11 dinner rolls, nobody gets to eat the dinner roll unless somebody says they don't want it. right? Because if everyone doesn't get the same thing, nobody gets anything. That's kind of the mantra that they go with there. All right, next, we're going to jump all the way up to aluminum, atomic number 13. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. And that is precisely what it says here. In the first ring of the Bohr model should be 2 electrons, and there are. In the second ring of the Bohr model, there should be, we'll count them, 2, 4, 6, 8. And there are 8 in the second ring. In the third ring, there should be these 2 plus this one, 3 total, and there are 3 in the outermost shell. Well, we might as well continue and look at all these. Hopefully it'll make sense. Argon's atomic number is 18. And so we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so it's 1s2, 2s2, 2p6, 3s2, 3p6. Now, notice in the second energy level, there's 8 electrons, and that's what we have. That's what's here. And the third, there's also 8, and we have 8. Atoms want to have a full, what's called stable octet, or 8 electrons in their outermost shell. And it turns out that only S and P are in the outer shell. D's and F's are never in the outer shell. So if you can see, if it ends with 8 electrons in the outer shell, that's a very stable atom, and it won't react very much at all. Well, if I went to fluorine, fluorine's atomic number is 9. We're kind of bouncing around here. So now we're putting in 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1s2, 2s2, 2p. We got 1, 2, 3, 4, 2p5. And that's what we're showing. Notice in the outermost shell, which is not the first, the outermost is the second energy level, there's these 5 and these 2, 7 electrons. In the outermost shell, 1, 2, 3, 4, 5, 6, 7 electrons. So that's not 8, which means it's not stable, and it'll work very hard, i.e. it'll be very reactive trying to get an 8th electron. Iron, we got to jump up quite a bit to get to iron. Iron on the periodic table is element number 26. So when we do that, we're going to put in here 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and then we get to come back 26. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 2, 3, 4, 5, 6. And that is exactly what we've written here. Now, if I said how many electrons does iron have in its outermost shell, the answer is not 2, 4, 5, 6, 7, 8. Because the outermost shell is the 4th ring. There's only in the 4th ring 2 electrons. These 6 are actually what we call part of the kernel. They're buried in the atom. They're not the outermost shell. And notice in the Bohr model, there's only 2 electrons in the outermost shell. Finally, if we want to get really, really silly, we could do lanthanum with 57 elements. And of course, you could easily fill these in, but I'll just go ahead and do that for you. You can trust me, that's going to be 57. I could have just looked at my periodic table, and based on its location, I notice it goes 1 in on there. So it has 1 in the 5D, and therefore it's relatively easy to come up with. We could do that way. All right. Hopefully that made a little bit of sense. A lot of this is going to come down to you just practicing all of this stuff. All right. Let's see what we got. Oh, there's a shorthand way, of course. You know, with everything, there's a hard way, and they always show you that first. And then after your boss gets to like you a little bit, they say, oh, here's how we really do it around here. So let me show you the shorthand, and maybe this will make some sense to you as well. Okay, so let's look here. We've got hydrogen. Now we know hydrogen is a 1s1. in terms of if we were to draw it out this way, if that is the 1s orbital, it has one electron and it would go spin up. Okay. Now there are other orbitals available for that, the 2s, the 2px, 2py, 2pz, the 3s, and then the 3p's, right? We have all those available, of course. Now, if we were to look at, and we only need to put one electron in, so I've left that one dark, so 1s1, excuse me. If we were to do the next element, helium, it has 2 electrons, so when those go in, it's 1s2. I don't need to use any of the other available orbitals. Okay, so those are all empty. When I do lithium, it's 1s2, 2s1, 3 orbitals. Excuse me, 3 electrons. So they go in. 2 in the first one, spin up, spin down, because Pauli exclusion principle, they have to spin in opposite direction. Then we have to move to the, again, using the off-bow principle, the next available orbital is the 2s. And we only have 1 electron, and by default we say spin up. So 1s2, 2s1. This is still not shorthand, I'm getting to that. These are not used. When we get to beryllium, beryllium's atomic number is 4. We're kind of going in order, so I'd have 4 electrons. So maybe you could tell me 1s, is it really 1s1, 2s2? Or instead, is it 1s2, spin up, spin down, 2s2, right? So I think that's a typo. I think I left it in there to see if people were paying attention, but it should be 1s2, 2s2, okay? Because we need 4 electrons. All right, let's try carbon. Carbon's atomic number is 6, so we need 6 electrons. So when we fill that in, it's going to go 1s2, 2s2, 2p2. So look, 1s2, up, down. Now we've used 2. That's full. So we got to go to the next energy level. Up, down, 3, 4. Now we got to go to the next available energy level, 5. Now we don't put spin down because of Hund's rule. We go to the maximum number of orbitals, so it goes in the next available orbital. So it's going to be 1s2, 2s2, 2p2, and that's its electron configuration. We don't use any of the other ones; they're not needed. When we get to sulfur, sulfur has an atomic number of 16. So how about 1s2, 2s2, 2p6, 3s2, 3p4? Notice that this pattern never really changes. That's the off-bow, the building up. So putting in my electrons, I got 16 electrons, right? So I go up, down, 1, 2, that's full, move on. 3, 4, that's full. 5, 6, 7, 8, 9, 10, that's full. 11, 12, full. 13, 14, 15, 16. And that should be the electron configuration of sulfur. So notice we don't have to do anything funny on the end. Now if you drew out, these are called orbital diagrams, if you would have put 2 here, and none here, it still would have read the same. It would have ended with 3p4, but it would be incorrect. So you want to make sure you understand how to fill in the orbital diagrams as well. All right, let's keep looking. We already did that guy. Now I'm just showing you that if it was a Bohr model, it would have 1 proton, 1 electron in the first ring, kind of keeping it equal for you. Here's our helium, 1s2, and if you were to draw that out in the Bohr model, it would have 2 protons in the nucleus, and in the first energy level, the first ring, orbit, it would have 2 electrons. One would go here, and the other one, I think, would have to go on the opposite side because electrons repel each other. If we were to do, and now this might be a new term for you, Columbic attraction. A coulomb is the smallest amount of attraction there is. It's the attraction between a proton and an electron. So the reason these electrons don't spin off the atom is they're being attracted by the Columbic attraction of the nucleus. The positive is attracted to negative. And of course, the 2 electrons don't want to be near each other because the same charges would repel. Here's beryllium. Beryllium, remember, has 3 electrons. It also has, 4 electrons. I finally drew it right here. It has 4 protons in the nucleus, In the first energy level, that's what this 1 means, there's 2 electrons. 1, 2. Now, these second 2 electrons are not in the first energy level. They're in the second ring or second orbit of the Bohr model. And so I put 2 more electrons here and here, and that's how I draw the Bohr model of beryllium. So hopefully you can see how the Bohr model might not be exactly 100% correct, but it still represents mostly what we need it to. And that's why it's still taught. All right. I'm going to get through and talk about the shielding effect and the kernel electrons much more in our next unit on the periodic table. At this point, we just want to learn to write electron configurations. All right, if we look at iron, all right, we've got our little filling order here, and iron on the periodic table is element number 26. So when I fill in the electrons, right, it has 26 of them. And when I fill them in, it's going to go in order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. What do the 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6 equal? I hope you said 26, because the superscripted numbers represent the number of electrons. Now, if we were to fill this in, all I've done is taking this arbitrary energy level and go from the bottom up, and I made it left to right. So filling in 26 electrons, it goes 1, 2, up, down, 3, 4, 5, 6, 7, up, 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 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now remember, everybody gets 1. 21, 22, 23, 24, 25, and 26. And that's how we're thinking about the electron configuration, filling in those orbital diagrams. All right. Let's try this one. On the Bohr model, there's our 26 protons. In the first energy level, here's the first energy level, 2 electrons. So we'll put those on there. In the second energy level, so I have these 2 plus these 6. So there's 8 electrons in the second energy level, and I'm going to put those on there. In the third energy level, see how I have these 2 plus these 6, that's 8. But I also have 9, 10, 11, 12, 13, 14. So it ends up having 14 electrons in the third energy level. And in the valence, or outermost level, if you know anything about house decorating, a valance is the thin little curtain that you put in the sheer in front of your window so people don't look in, right? In the fourth level, the outermost level, there's 2 electrons. 1, 2. Now, it turns out that iron would like to lose those 2 electrons to have a full outer shell, and that's why it ends up getting a positive 2 charge. And we'll discuss that more, again, when we get into the bonding unit a little bit later. But I want to show you where this is all going. And finally, here's some shorthand, right? Now, if I write neon 3s1, using a periodic table, you can find that the third period, the S block, the first element, is sodium, element 11. So when I look at this, if you were to write out sodium, it would be 1s2, 2s2, 2p6, 3s. That would be it. And then if you add a 3s1, then you're going 1 pass of sodium to neon. So here's how it works. On the periodic table, you find your element. Then you find the element that is the noble gas that comes before your element, and you write that in parentheses, and then whatever comes after that you have to add. So when I do this, I could write out neon as 1s2, 2s2, 2p6, 3s1, or in shorthand, for sodium in shorthand, I misspoke earlier. Sodium in shorthand is just neon 3s1. So looking at this, when we fill all this stuff in, the first thing, the letter A there, that represents neon's electron configuration, the 1s2, 2s2, 2p6. So you never have to write a noble gas's electron configuration. Then the 3 here represents that the outermost electrons go in the third energy level. And it must be an s orbital, and there is 1 electron in that orbital. So that's shorthand. when we're in class, when I can write on the board, it's going to be a lot easier for you to understand shorthand. Okay? Now, let's see if we can practice this stuff, some shorthand configuration. If you have a periodic table in front of you, it's going to make it a lot easier. So I'm looking for what ends with a 4s2. So I have to go to the fourth period, the S block, the second element in. Well, that to me looks like calcium. So I'm going to go ahead and put a Ca there. All right. The next one is vanadium. Now I know you're not real familiar with the periodic table, but it's element 23. So in order to get to 23, that's in the fourth period, I have to go to the noble gas that precedes that element. Well, that's in the third period. The noble gas is on the far right, so I'd write argon in brackets. And as soon as I write argon in brackets, that takes care of the first 18 electrons. Then I follow that with a 4s2 and a 3d3. So argon, 4s2, 3d3. Again, you may have questions on this, and we can talk a little bit more in class when we meet. All right, look at the next one. I've got a helium, 2s2, 2p5. So I find helium, then I go 2s2, I use lithium and beryllium, and I go 5 p orbitals in the second 2p block. So I count out boron, carbon, nitrogen, oxygen, and fluorine. So it looks to me like that's fluorine. All right, next we have silver. Silver is element 47. So the noble gas that comes before that is krypton, and that takes care of the first 36 if you write Kr in brackets. Then you write 5s2, and then you have to count. You're in the 4ds, and you got to count 9 over. So how about krypton, 5s2, 4d9. Next, we have iodine. Iodine is element 53. So in order to get there, the noble gas that precedes it, again, is krypton. So I write Kr, that takes care of the first 36. Then I have to go to the fifth row. So I'd say 5s2, that's rubidium and strontium. Then I go 4d10, and then I go 5p, and I have to count over 1, 2, 3, 4, 5 squares to get to iodine. So how about krypton, 5s2, 4d10, 5p5. Now that's actually a lot easier than writing out the entire thing, isn't it? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. Whew, that's a mouthful to get that all out. Now, don't shorten this up and just write 5p5. That's not what I said to do. That's going to be incorrect. Now look at the next one. It ends with a 5p6. Well, 5p6 is xenon. So, quite honestly, you could write it this way, but nobody's probably going to ask you the noble gas of shorthand of a noble gas. They know what it's going to be, so I won't do that either, probably. Now, the next one, somebody did, but they didn't do it correctly. Right? They used shorthand, or what they thought was shorthand, and it ends with 3d6. Well, 3d6 is argon. Okay? So the noble gas that precedes that would be neon, not helium. Whoops, excuse me. I was looking at the wrong thing. I was looking at 3p6, not 3d6. 3d6 is indeed iron, and the noble gas that precedes that is argon. So instead, what we should have written instead of this is we should have written argon, which takes care of the first 18, followed by 4s2, and then we count over 6 squares, 3d6. Seaborgium, boy, that's a tough one. Element 106, right? Now, I'm going to put it on here for you. In shorthand, it always raises a few questions, and we can talk about that one if you wish some other time. All right, that is it, folks. Hopefully you have a little bit better idea of electron configuration. Again, you need to be able to do shorthand and longhand using the correct filling order. We'll do some more practice with this, and hopefully you'll have this all figured out. Good luck with electron configuration. Bye-bye.